Sir, welcome everyone to the fifth session of webinar. I am Madhumita going to host today's session. Hope I am audible to everyone. If anyone have connectivity regarding problem, you can text in the chat box. So I'm gonna give you a short brief introduction of Mr. Prajnajyoti Mazumdar. So one of our ISM alumni of MSc Tech Applied Geophysics 1998 batch. He started his career at Reliance in 1998. He has been on seismic crews and processed seismic data between to the newly set up QI team at Reliance. In 2006, he decided to quit his job and with his wife and daughter embarked on a new journey at Colorado School of Mines to pursue PhD. He received PhD degree in 2010. During his PhD, he developed non-converted CRF imaging and analysis technique for tight cast sand characterization using 9C 3D VSP data. He also developed seismic virtual source for detection of fracture in reservoir rock using 3D VSP data. After spanning 10 years through several challenging projects, currently he is pursuing a great career as researcher in oil construction engineering team at Exxonmobil USA. His newly developed aspects of subsurface engineering enable to achieve superior business results. He was also a former board member at Elsevier Science Journal of Applied Geophysics. Today he is going to deliver a lecture on borehole seismic technology. So sir, now it's over to you.
Thank you so much. Welcome everybody. Good morning, everybody. Today I would like to share some talk about whatever I have learned over my past experience, and I have tried to bunch everything in a particular presentation here, and you can hopefully get something out of it. This is a technology. This is not taken very lightly in energy industry, and when we handle this type of technology, because it is cost intensive, it has to be practiced by proper geophysicists who really understand seismic in its entirety, subsurface in its entirety. And I would try to explain how borehole technology is useful and what we can get out of it at its maximum. Okay. So today I would talk about the fundamentals of borehole seismic technology. I would explain what is a VSP, what are the common VSP survey designs, what are the applications of VSP in real world, and finally, you should be able to understand the cost benefit in business settings so that as a professional, you should be able to make a decision whether to pursue a certain VSP project or not. And if so, then what type of VSP you should pursue. So let's go to the first one, the fundamentals of borehole seismic technology. So this is how the borehole seismic technology looks like. This is a typical setting, like you have a well here. It's a vertical well, simplest thing. You have some hydrophones or you have geophones planted inside the borehole, and you have a shot put somewhere near the rig. This is called short offset. Short offset means 20 to 50 meters of distance from the rig. You just don't want to put a source at the rig. It is slightly away to keep the rig safe. We call it a zero offset VSP. It is not essentially zero offset, but because the distance of the source from the rig and the vertical distance, this ratio is very small, we essentially call it zero offset because the waves are all propagating down, almost vertically down. So it is called zero offset VSP. Another option is you have the same hole, but if your source is far away, that is called an offset VSP. That's no more a zero offset. Now, what if the wellbore is deviated? Then how do you get a zero offset VSP? Because you have drilled the well, you know what is the trajectory, and you can put seismic sources right above the receivers, and you can get almost vertical incident waves. There is offset VSP in a deviated wellbore. You can do that. There are various types of offset VSPs. If you have horizontal well, you can have offset VSP like that. Fundamentally, all it means that you should have a certain distance of the source from the rig or source from the receivers. They are far away from each other. So all these waves are being incident at an inclined angle. That is what is the role of offset VSP. Different VSPs are, of course, used for different reasons. I would explain that later. Another option here is a drill bit listening, means you are drilling it here, and at depth, the drill bit, because it is cutting rock, it is generating seismic signatures, and you can record it near the well. And it is possible only when everything else is very silent, you can record signatures here on the surface. This is not very common. The other one is a walkaway VSP. So let's say you have one sensor here in the well, and your source is moving out. That is called a walkaway, as if you are walking away from the rig. That's called walkaway VSP. In a deviated well, this is the picture. You have a source, you are still walking away, you are measuring signatures. Walk above is essentially like you are directly above the hydrophones or the geophones in the well, and you are recording the signatures here at the well. If you have two wells, that is called cross well survey. It was very popular when I was a student 20 years back, and now no one does it. It's very expensive. So you have two wells. One well is hosting the seismic receivers. One well has seismic sources, and you fire from individual source and get recording at other receivers in the another well. That's called cross well survey. Then there's the intra well survey, as if the source is inside and the receivers are on the horizontal section in this well bore. These type of configurations are not common, because once you put a source inside the well gets destroyed quite a bit. You do not want that. Well is the most expensive asset you have, so you do not want to destroy that. Then there is an inverted VSP. Inverted means you have source inside, receiver outside. Again, this is not very common. All of these require a borehole. It's very expensive. These wells are the most expensive operations in the oil industry. And seismic sources and receivers are needed along with the well bore. Seismic sources are not expensive. Receivers are moderately expensive, but not that expensive. The well bore is the biggest thing. Okay, so whenever you propose a VSP, because of the well bore, people make a decision whether to go or not to go. Continuing on what is VSP, we are talking essentially about recording seismic waves deep inside the earth before it reaches the surface. So if you have a seismic source on the surface, if you shoot a seismic source, the wave is going to go down and supposed to come back. But before it comes back, you capture it and record it in a well bore. That is VSP. Okay. It needs a host of geophones inside the well. Without geophones or hydrophones, you will not get any signature. You put that here. You need around 60 to 100 receivers in the borehole so that you can get quite a good coverage or recording inside the borehole. If you have very sparse hydrophones or geophones in the wellbore at quite a bit of depth distance, that data becomes sparse, and that is conveniently called a check shot survey. Check shot survey essentially is used for time to depth conversion. You can have active sources on the surface, or you could have passive sources in the subsurface. Let's say you have a reservoir here, and the reservoir is producing, or you are injecting inside the reservoir. When you inject, because of fluid movement or the stress changes in the reservoir, it creates seismic waves. You can record that seismic wave in a nearby borehole, and you can try to understand how the fluid front or the pressure front is moving inside the wellbore, if that is the purpose. Also, I would like to share what different types of waves are. There is one wave from the seismic source straight to the receiver that is called a direct arrival. Then there is a wave that would hit some kind of boundary inside the subsurface, go back up, because it is air rock interface. It's a very strong contrast medium. It would reflect back again and get recorded. That is called a downgoing multiple. This wave is called downgoing multiple. It would come little later, but it would have something very similar polarization like this wave. Then there's an upgoing reflection. You shoot a source, this goes down, hits the target, and gets recorded after a reflection. And there is an upgoing multiple, means a wave comes here, hits a subsurface layer, goes back up, hits another layer, comes back up, comes down, and then goes back up. It's like W form. All of these waves are recorded simultaneously, whether you like it or you do not like it. Okay, so why VSP? You talk to a manager, he gets alarmed instantly whenever he hears, okay, these guys want to acquire VSP. And it is expensive because you are holding a well for acquiring this data. So when it is expensive, they say it better be useful for business. So when we do VSP, a good geometry is very important. When I say geometry, means how the well is drilled, whether it is vertical or deviated, whether you will have the geophones, because the well is long well, let's say 3 or 4 kilometer long well, where you want to put the receivers. And when you put the receivers, where the sources on the surface should be. All of these constitute the geometry of your survey design. Okay, so why VSP? VSP records high quality seismograms. In other words, when the receivers are in the borehole, you will have low cultural noise. Unless there is another drilling activity going on somewhere, you should have very low cultural noise, no noise at all. That means very good signal to noise ratio. You will have a direct measurement of travel time. Because you shoot a wave, you will have the wave reach after a certain time. That is called travel time. Direct measurement of travel time and wave polarization. So when a wave passes through the subsurface or any medium, you will see it has a polarization. Means it moves a particle along its path in 3 dimensions. So in which direction it is moving is told by the wave polarization. That's important in velocity model building and evaluation of the anisotropic nature of the rocks. Because the particle motion would be determined by the rock property itself. Which direction it would move depends on the anisotropic behavior of the rock. Detailed seismic imaging near the borehole. That is what is usually that is the most important reason why people do VSP. Okay, it tells us about reasonably precise reservoir geometry near the wellbore, gives you some idea about the heterogeneity, the fluid movement in preferential pathways inside the reservoir. All of these things you can understand through a properly designed VSP survey. It also helps you understand what is the attenuation behavior of the rock. Because you shot a seismic source on the surface, the wave propagates down, it gets attenuated. High frequency gets attenuated quicker than the low frequency. It gets attenuated. You can measure how the subsurface is behaving in terms of attenuation. You can measure that attenuation. These are the common uses of VSP survey in energy industry. So what is the common VSP survey design? Let's talk about it a little bit more. The most common is zero offset VSP, as I told you earlier. You don't have to do anything, just put a tool, shoot an air gun on the surface or a little small charge dynamite source on the surface, and you'll record it. You would know a lot about the subsurface already. But this happens when the things are very simple along the wellbore or near the wellbore. And if your problem statement is very simple, at what time, at what depth, that type of measurements are useful. Zero offset VSP. Offset VSP is not that common. Is done under very specialized requirement, but that's another design where you put the source away, you get the direct wave, you can measure certain thing here. And of course, you have to do few more shots, like in walkaway VSP, you put some more shots here. You start knowing a lot about the subsurface as the source starts moving out. Then there's a walk around VSP. You have a well, you shoot along this line, and then change your direction and shoot again, change the direction, shoot again. You can have 3 or 4 lines passing through the well. That is called walk around VSP. You are walking around. Sometimes you can also move around for efficiency purposes. Basically, you decide at what shot locations you are going to put a source and acquire it that way. So it gives us a very good azimuthal and polar coverage for a given reservoir or a given target. You can have a walkover VSP. People do it to understand the lateral heterogeneity as well as the vertical velocity. But you need tomographic techniques to do all this. So you're slowly getting in a little bit more complicated processing techniques if you are acquiring specialized VSP. And the last one is drill noise VSP. People barely use it these days, but it's an option. It works for shallower formation because as you go deeper and deeper, the bit does not give you enough signal to be recorded on the surface. So it is usually used for shallower applications. Then there is something called salt proximity VSP. Let's say you have a salt dome. You have reservoir near salt dome. You know that there is a salt, but you do not know precisely where it is. So you have drilled a well and you want to know where exactly is that. Then you put seismic sources on the surface and you'd use certain types of waveforms to try to understand how far the salt flank is from the well. So this type of survey is called salt proximity survey. And the most generalized is a 3D VSP. You have a well, you have multiple receivers here, and you can have seismic sources going all around. That is the most comprehensive data you can get. That is called 3D VSP. It can see quite a bit away from the reservoir, still near the reservoir, but quite a bit away. And it gives you very good quality information if the problem statement is like that. Now let's talk about some applications. What do you do once you have the data? So the most important thing VSP does is the velocity modeling. So this is an example of a VSP acquired in a vertical well. And let's say this is the vertical component of a geophone, means it is recording all the waves that are vibrating in a vertical direction or predominantly in vertical direction. So you have the seismic signature. So vertical axis is depth here, horizontal axis is time. So individual lines that you see here are all seismograms. They are a collection of seismograms. And here is like the vertical coverage is 900 meters. That is quite a bit, for example. And this is giving you the first arrival. That's called the downgoing wave. The downgoing wave is this type of slope, and there is an opposite slope. Those are all reflections coming. Means you have a reflector at these locations where the upgoing and downgoing meet. Okay, so this type of geometry is very good for you to understand what is the vertical velocity. So you know that there is a receiver here, there is another receiver at a different depth, so you know what is delta D. You have a difference in travel time, that is called delta T. You can do a simple math and get what should be the interval velocity between this depth and this depth. You can make it as fine or coarse as you want. This is a simple example of a zero offset source vertical well VSP. It essentially used for time depth conversion and to generate VSP corridor stacks. VSP corridor stacks are basically, they look like 1D synthetic, but basically acquired or processed from this type of data. It gives you the exact time and depth of where the seismic reflections are coming from. So that is useful when you have surface seismic and you have VSP. You want to really know where is the reflection coming from, because not everything in surface seismic is actual primary. There could be multiples. And this type of surveys are useful to understand which are primaries, or which are multiples, or which are noise. This is a very useful application. Now, what else can we do to understand the directional velocity of the rock? Because rocks are not having the same velocity in all directions. If you have a horizontal layered rock, if it is, let's say it's a shale, and underneath shale there is a reservoir, that shale would exhibit directional dependence on the velocity. And when you have that, how do you know that what is the actual behavior of the rock without actually taking the rock out and putting in the lab and then measuring it and then having some sort of a scale problem, like, okay, this little rock, how this may not be representative of a very thick vertical section. How about we develop a technique so that we can understand what is the anisotropy of the rock when we have an option to instrument the well and have sources on the surface. If you have a source on the surface, this wave is encountered, recorded here, another wave recorded here. So you know what is time difference, you know what is the depth difference, you can compute what is the slowness, that is the vertical slowness. And because the wave has come in a certain direction, it is going to move this particle in a certain way. It would vibrate in the certain way. And when it does that, you can find out what is the polarization angle. And using the polarization angle and the vertical velocity, you can compute what should be the slowness. Because you know the slowness, you can now invert for anisotropy properties that controls the slowness and the polarization. So phi here is the polarization, Q is the slowness of the P wave. That is being controlled by Thomson's anisotropy parameters. And this is for a weak anisotropic medium. Like if the rock is very mildly anisotropic, then this is the approximation that works. So you can compute you can estimate what should be the anisotropy here. Why do we want to use the anisotropy? This anisotropy would help you process the seismic data in a little better way. Because it is a VTI assumption, vertical transverse isotropy assumption, means you have a vertical symmetry axis. The rock velocity changes only in different angles about the vertical. You can use that behavior of rocks for processing data where your geology is predominantly flat but anisotropic. So you can use this VTI property for processing. Now, what you see on this plane can happen in another plane also if the rock is fractured or if it is encountering significant lateral stresses. Then the rock does not stay VTI, it becomes orthorhombic. But you can apply the same principle in another direction, let's say orthogonal to this direction. So you can put your source in another direction and you can estimate the anisotropy parameter in that direction. That would build your total orthorhombic velocity model. So it's pretty generalized in that sense. All right. So now, what if the subsurface is too complex? In this example, subsurface was not that complex. It was just anisotropic. But what if the subsurface is complex? When I say complex, means there is a strong lateral velocity variation. Means there must be something that is causing that. And this example is showing a typical example in Gulf of Mexico like setting where you have a salt dome and you have the reservoir underneath the salt dome. How can we know better under the salt when seismic is completely busted out? If any one of you have seen seismic underneath a salt, you would know how difficult it is to understand what is the geometry underneath the salt, unless you have a very specialized seismic survey being carried out. Sometimes seismic surveys are delayed. It is easier that there is a well. They can instrument the well and quickly shoot on the surface. They would put a boat and run around the well and acquire a survey and understand what is the nature of the reservoir and how the stratigraphy of the reservoir is. So people have thought about this. There is another specialized part in geophysics called seismic interferometry. So seismic interferometry, what it does is actually it takes the seismic wave field recorded from seismic sources on the surface. Let's say you have a well here with geophones planted here. They're all under the salt. Very difficult to see geology here. You want to know what exactly is happening. Ideally, you would think it would be best if my source is underneath here rather than on the surface. If my source is here, then it will not see this salt. It would see here, it would shoot from here and get recorded here. It would shoot from here and get recorded here. It can shoot from here and get recorded. It can do all sorts of things if we can put the source down. But that is physically impossible. If you put the source down in this expensive well, it's going to bust the well. You cannot do that. So what you do is you need to do something mathematically fancier and physically more interesting to understand what we can do so that we can numerically put a seismic source here. So this example shows a generation of virtual sources. Virtual sources, they are not real sources, okay? They are virtual sources. They are put here and it would fire from underneath. So how do we formulate that? So think about, like, we have a seismic source here and the wave passes through the salt dome and gets recorded in the borehole. So that blue is that particular leg which is recorded in the borehole from the real source. There is a direct arrival also that would happen from the same source to these receivers, and you can identify these wave paths in a seismogram. You can reasonably well do that because this would reach the fastest and the others would reach the slowest. So you can understand where is your main arrival, the direct arrival coming versus the reflections coming. So the purpose is to find out what should be the formulation so that our source is here and receivers are all, everything else is inside the borehole. Okay, so we take this seismic source and we take the direct arrival. We take the direct arrival, reverse time it. Means if you are recording something as a time series, you reverse that thing. Just reverse the matrix. Convolve with rest of the seismogram, and then sum for all the sources. Do this summation for all the sources. Let's say you have 100 or 200 sources. You just sum them. What you would get is you will get a seismic source that fires from here to here. That is very smart. That is very smart. If you can do that, you completely get rid of the effect of the overburden. Because if you have a source here, it does not know where is your overburden. It just fires from here and records here. And you can do that for every receiver. So what it does is when you have source in the borehole and receivers in the borehole, it is going to image reasonably well wherever is the target. Also, the more complex the overburden, better it is for the quality of estimated velocity and imaging. Means this expression would be much more successful if your overburden is very complex. When your overburden is complex, this wave will not pass on this plane. It would pass through your 3D geometry and come back here. Same thing would happen here. So basically, you will see that the wave from different sources are arriving at different angles. When they arrive at different angles, it is facilitated by a very complex velocity model. When you have a complex subsurface like this, you would have adequate coverage from here to here. And that makes this technique very successful. This is very contrary to the conventional wisdom, because if it is complex, you would think that every method would fail. But this method uses the complexity of the rock. And it succeeds. More complex the overburden, better it is for you. Now, what if the subsurface is too complex and we want to know fracture direction in the reservoir? So your shallow part is complex and we want to know something in more detail underneath this complicated overburden. How do we know? Can we do something that we learned from the prior VSP studies or the prior VSP know-how? What can we do? Because we are talking about details of the reservoir, our wave field input should be also very complete. When I say complete, means we should be able to record all types of directions and all types of polarizations and all types of waves. And we need to use it as detailed as possible to understand what should be the subsurface looking like. Okay, so this is a well. We have a complex overburden. The complex overburden has different fracture orientation, but our reservoir of interest has another fracture orientation. How do we know that? So we can use our prior knowledge, this knowledge, in understanding the subsurface. Because now we have a complex overburden, and because we have a borehole, and we have receivers in the borehole, we can use seismic interferometry to bypass this complex overburden and try to shoot right underneath it and try to understand what is going on in the reservoir. Okay, so one such survey is called 9-component VSP. If the sources are moving around the well, it is called 3-dimensional 9-component VSP. 9-component VSP means you have 3-component sources and 3-component receivers. What do you mean by components? Component essentially is the direction here. So 3-component source means the north, south, east, west, and vertical. Means you have directionality to the wave motion that you can create. And what are those equipments that we can use? We have vibro-sized trucks. Those are specialized vibro-sized trucks to put the plate down and shake it in a given direction that you want it to. So it can shake in north, south, or any other direction, then go to orthogonal and shoot in another direction, and it can also shake vertically. So this type of seismic sources are called 3-component sources. And you already have 3-component receivers in the borehole. So 3-component sources and 3-component receivers with 3D source points. 3D source point means there are all types of source locations away from the well, near the well, away from the well, and it moves around the well to give you complete azimuthal coverage to the source points. So that is about 3D 9-component VSP. Okay, you can use, we use this technique to generate virtual sources underneath this complex overburden, and it shoots exactly like any other vertical VSP. Look at this. This is a shear wave coming. This is a shear wave coming, because we generated waves that would shake in only one direction and in another direction orthogonal to it, and it will show you how it would be recorded in any other level below it. So this one is shaking in one direction and recording in the same direction. This one is shaking in one direction and recording in another direction. So you are not seeing it because the reservoir is not splitting it anymore. We have found out a direction in which we have found out the correct polarization. Do you guys, if you guys do not have background in shear wave splitting, I would like to give a very quick idea. What it does is, if you have a randomly oriented shear wave passing through this rock, what it does is it breaks it into 2 waves. One would be a slow wave and another would be a fast wave. And that happens because the rock is more compliant in this direction than in this direction. So the velocity of this direction and the velocity in this direction would be different. And that is why you would see shear wave splitting. And this is very important to understand which direction the fractures are oriented and in which direction your stresses could be oriented. It is a play of both of those things that the receiver would see. So you will see one wave arriving little earlier than the other. And that little difference is impossible to know if you just analyze seismic sources on the surface and try to understand these waveforms here. You cannot see them. They would be all randomly oriented, and it is a big mess when you see the actual seismogram. You want to make it simple and explainable, and that's why the virtual source method is very useful. You can orient, you can start rotating the seismic signatures in a way so that you will see this directional dependence of reflectivity. Then you would know wherever it peaks or wherever it goes down, you can find out which direction it is fractured. This is just an example to show how a seismic virtual source trigger time starts and how the fast waves come earlier than the slower one. So this is possible because we have a complete polar and azimuthal angle and offset coverage from the survey geometry. If you do not have enough sources, you cannot do that because you need enough sources to sum across. Because remember this summation should be at least 100 to make it a good signal to noise ratio seismic source. So to make that happen, you need to have 100 sources on the surface. That is expensive. You need to hold the well for a long time to shoot 100 sources properly because each source location, you are shaking the ground in 3 different directions, and there is a time to acquire that. It takes time and it is cost. So let's see how this type of geometry can illuminate the subsurface. So the problem statement here is, what if the reservoir is not clearly visible on P-wave seismic? If you have a shale and sand properties very similar, the P-wave property very similar, the seismic survey cannot see where is your sand, where is your shale. It is essentially transparent. Forget about details. You can't even see that. It is below the detection limit. So when such a case arises, shear wave property could be very useful. When you have shear wave property that has a contrasting relationship between shale and sand, it makes sense to put this type of survey, and then you can see how the sand channels or any other feature that you are targeting, you can eliminate out. So this example shows a fluvial channel complex for a recording in a well that was positioned here. The well was here, and it is able to see quite a bit away, depending on how the sources and receivers were. The sources were all in here, receivers were all moving around. So it could see quite a bit of the subsurface like this. You also get a fast and a slow image. Remember, I mentioned about there is a fast wave and there is a slow wave. Both of the waves would create their independent images. And it can tell you, because this is reflectivity, imaging is reflectivity, it will tell you how the reflectivity of one direction shear versus the overburden or the contrasting material amounts to. These type of exercises are important for development setting. They are not for exploration. So these are very specialized tools, specialized procedures. But this is the technology that has the ability to show you how to see away from the well in different shear properties for the same reservoir. So in this example, because the rocks were fractured nearly vertically, we had to build a HTI, horizontal transverse isotropy velocity model for imaging. And that helps us to get this type of images. It gives a fast and slow shear wave images simultaneously. So let's understand the cost benefit for these VSP surveys in business settings. So in real world, when you go for this type of surveys in a deep water setting, you will have a daily rig rental of around 300,000 to 550,000 US dollar. 1 day rent, just the rig. There are equipment and other associated costs that we have not considered here. It can easily blow up quite a bit for a survey. Because you are stopping the rig, you don't let it drill or do anything. You have to stop the rig. The well is stopped. That is a cost to any company. Unless there is a reason, they would not spend this money. So this type of cost needs to be taken into account when you design a survey. When you pose a problem statement, why you design a survey, to achieve what. These things are important during a discussion. All the noisy rig machinery are in standby. If you want a very a noise-free environment for your VSP recording, you need to stop all the machinery, including generators and everything on the rig. Make it as calm as possible and then shoot it. Now, giving an example, the cost of rig standby for a vertical zero offset VSP is just few hours, maximum 6 hours, depending on how much coverage you want. This is a quick thing. So you will get approval for this thing. No problem at all. Now you start talking about offset VSP. Now it would take you almost a day. Almost a day means this type of cost you are talking about. And if you just tell them, hey, I'm just going to measure anisotropy in this, unless the anisotropy is giving you deep trouble, they would not approve even this cost. Now you talk about walk around VSP is more than a day. That would make people really, really worried. If you talk about walk around VSP, that would take more than a day. It would be expensive, very expensive. And 3D VSP will take a week or so, could be 10 days or more, depending on how big the survey is. So what do we get out of all this? 3 to 6 hours, it is a quick thing. The deliverables that you would give is a velocity depth function. You'll get the corridor stack. You'll get some idea of attenuation if you want to. This is a cheap activity. This is easily approved. No problem at all. Here, you will have velocity depth function you will get. If you have few more receivers here, you will get a very good velocity depth function. You will get VTI anisotropy also, and you will get a 2D VSP image along this line or along this plane. This is still okay. I mean, if you have a deep water well, VTI anisotropy is messing up with your imaging, subsurface seismic imaging, then they would probably approve this. Now start talking about walk around VSP. In my career, I have just seen one walk around VSP, that also in an oil field that is a super giant oil field. No one wants to do this type of thing. And then there is a 3D VSP. 3D VSP is somewhat common in Gulf of Mexico. This is just because the subsurface is difficult. If you really want to know what is happening before you put an investment. But you get quite a lot out of this. You get a 3D VSP velocity model. You get a VTI or orthorhombic anisotropy parameter. Excuse me. You also get attenuation model because you have all types of sources, all types of angles, direction. You get an attenuation model. And above that, you get a 3D image. That is a big thing if planned properly. So you get quite a bit out of it. But if it is costing you like a week or 10 days, think about what would be the cost here. Multiplied by 10 days, maybe $5.5 million. Your resource should be big enough to put that money in there. So that's all I wanted to share with you guys. If you have any questions, I'm happy to answer.